Hello, my name is Dexter Hine, and today I will be presenting the exciting possibility of muon colliders, why we might want one, and what problems stand in the way of us getting one. In a collider, beams of charged particles are accelerated magnetically and put on a collision course. When the particles collide, their combined energy goes into creating new particles, which can be studied via detectors. If the history of particle colliders has taught us anything, it's that new and exciting discoveries require higher energy collisions. Over the years, larger and larger colliders have been built to find new particles and examine the behavior of particles that we've already discovered in finer detail. In the table visible on this slide and on the accompanying graph, there's a clear distinction between lepton colliders and hadron colliders. The hadron colliders tend to operate at higher energies as opposed to the lepton colliders, which here are just electron-positron colliders. The LHC is the pinnacle of particle accelerators, with beams of protons that collide at 14 tera-electron volts. This is the collider that first detected the Higgs boson. Using hadrons has its drawbacks, though. At these high energies, the protons undergo inelastic collisions. The constituent components of the protons, the gluons and the quarks, collide with each other. This produces collisions across a wide range of energies. This shotgun approach can produce high energy collisions. However, it's hard to create collisions at the precise energies you want. Lepton colliders offer significantly more control over the energies of the collisions as opposed to hadron colliders. Since leptons are fundamental particles, thus are seemingly not made of smaller components, all of the energy of the colliding leptons goes into an individual collision. One can consistently get collisions at the same energy, facilitating producing particles at that energy. A further consequence of the precision of this approach is that particle beams don't need to be as energetic, since none of the energy is being lost to collisions outside of the desired energy range. The cleanliness of the lepton collisions as opposed to the hadron collisions is illustrated in the two diagrams on the slide. On the left is data from the LEP, which collided electrons and positrons to create a Z boson, resulting in two neat jets, whereas on the right is streams of particles in a simulation of the LHC. You can see how messy it is. There is a catch, however, for lepton collisions. Charged particles accelerating emit electromagnetic radiation. The acceleration of a particle in a synchrotron is its velocity squared over the radius of the synchrotron. When the effects of special relativity on acceleration are taken into account, the power required to accelerate a charged particle increases dramatically as its velocity approaches the speed of light, since both velocity and gamma appear in the fourth power in this equation here. Muons are about 200 times heavier than electrons, though. Because of this extra mass, their collisions are roughly 200 times more energetic than electron collisions. The LEP reached energies of around 209 gigaelectron volts. If it were colliding muons instead of electrons at the same speed, it would produce energies of 43 tera-electron volts, while having the same losses due to synchrotron energy. The International Muon Collider Collaboration suggests that a 10 TeV muon collider could produce data comparable to a 100 tera-electron volt hadron collider on a much smaller footprint. One key component required to make a muon collider is a source of muons. At the International Muon Ionization Cooling Experiment, or MICE, at the Rutherford Appleton Laboratory in the United Kingdom, this capability is being demonstrated and refined. For a collider, ideally one would have access to a large number of high-energy muons. To create these, at MICE, protons are accelerated in a synchrotron and are fired at a large target. These collisions create bunches of particles including muons, pions, and kaons. Because the plus and minus pions interact with the weak force, they decay into muons far more frequently than electrons. The pion is a spin zero particle, The weak force only couples with left-handed chirality particles and right-handed chirality antiparticles. So the antineutrino produced in this decay must be right-handed. Since the neutrino's mass is small, its chirality state is approximately its helicity state. To conserve angular momentum, the lepton produced in this decay must also have right-handed helicity. The lepton helicity state can be decomposed into right and left-handed chiral components, but only the left-handed component contributes to the matrix element. This leads us to equation 11.19. Since both muons and pions are more massive than electrons, the matrix element for the pion decaying into electron is small. Because muons are roughly 200 times more massive than electrons, they are much more likely to be produced in this decay. The muons once created have a wide range of velocities and energies. In order to create a useful muon beam for a collider, the beam ought to be narrow and the muons ought to have the same energy. In order to accomplish this, at MICE, they are conducting ionization cooling. As muons pass through a material, they lose kinetic energy, their lateral motion is diminished, and then they are magnetically accelerated in the same direction, creating the desired narrow muon beam. The major difficulty with this process is the short lifetime of the muons. The muon's lifetime is about 2.2 microseconds, which doesn't give much time to properly order them into the uniform narrow beam and accelerate them to 5 tera electron volts for a collision. For this reason, cooling has to be a very quick process. Special relativity does help us out, however, since at high speed, the muons decay slower. One problem with such an accelerator is the high energy neutrinos it would emit. The muons that decay in the collider create neutrinos that radiate outwards in a plane of the loop. Due to their high energies, they are much more likely to interact with matter than solar neutrinos. This is because the cross-section of the interaction between neutrinos and nucleons increases proportionally with the energy of the neutrino. These neutrinos can pass through kilometers of soil and still cause harmful radiation when they pass out the other side. The figure on the right is from a paper by N. V. Mokov and A. van Ginneken, in which they simulate the radiation given off by muon colliders. The red line shows the amount of soil the neutrinos have to pass through in order to reach the Fermilab offsite annual dose limit. The red line shows the dose limit, I should say. The same paper suggests that one way of mitigating the radiation is to wobble the beam using a magnetic field so that the radiation emitted is not all concentrated on one plane. Sometimes the solution to pollution is dilution. The figure shows that a field strength of about 0.4 teslas brought the safe distance down to around 13 kilometers from 60 kilometers. This solution is much more feasible than putting the collider in space where the neutrinos won't have many nucleons to bounce off of. So what are the plans for the future? Both CERN and Fermilab have proposed building muon colliders. However, there are still technological hurdles to overcome, such as muon cooling. As such, there is no timeline for building a muon collider. How about a tauon collider? At 1.77 gigaelectron volts, tau particles are much more massive than muons, which would potentially allow for a much higher energy collider. Unfortunately, their short lifetime of 2.9 times 10 to the negative 13 seconds makes them infeasible for this purpose. And some conceptual questions. Why is synchrotron radiation more problematic for electron synchrotrons as opposed to muon synchrotrons? And what makes the neutrinos emitted from the muons in a muon collider potentially dangerous? The answer being, since electrons and positrons are less massive, they require higher velocities to reach the same energy as muons, which leads to more energy loss to synchrotron radiation. And for the neutrinos, their high energies increases their cross-section in nucleon collisions, and causes those collisions to emit more radiation. Thank you for your time, and I'm done.